Let's talk about error propagation using differentials. So this is called error propagation. Here's what we're going to do. We're going to assume that we are building a box. So build a box. And in our box, it's going to have to be a cube. Okay? We're going to say that the sides are x. So each side is x. Now, our error is that when we build this box, we realize that our machine is a little bit off. So each side is supposed to be x equals 4, but our machine's off a little bit, so it can be off, let's say 4 inches, okay? So it can be off by 0.03 inches, all right? So each side can be off that much. Now let's see what happens in terms of the surface area. We could do volume, doesn't really matter. We're just trying to figure something out here. So let's deal with the surface area. If you recall, boxes have 6 sides. So the surface area is going to be like this. Here's x, 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 and here's our box. It drops down here, and, you know, stuff like that. So all these sides are x. Now, the surface area is going to be this front surface or the side surface. They're all x by x. So it's going to be 6 times x squared in this case. So here's our surface area. Function s of x is equal to 6x squared. Now, if we have an alteration in our x value of 0.03, then that's something we'll use a little bit later. But normally, if we have a perfect box, if it's not messed up, our perfect box is going to use how much cardboard. You know, boxes are made out of cardboard usually, so we're going to say that. Well, a perfect box uses s equals 6 times, if x is 4, we would have 4 squared, which is 6 times 16, or 96, and that would be in inches squared. But our box is not perfect. So how about the errored box or the altered box? Let's check that. Our altered box is going to have a possibility of some error. So using differentials, use differentials to estimate. Differentials look like this. The actual surface area plus what we call ds, the alteration, is approximately equal to the original function. So that would be 6x squared, okay, plus, now what's ds? Well, ds is what we get from s of x's derivative. So s prime of x is equal to 12x, and then we throw in dx, the alteration there. Now that comes from saying ds dx is equal to 12x and treating it as if it's a fraction. It isn't really a fraction, but it works well treating it that way. So we put this over here. So we're going to call this 12x dx. That's the style for differentials. So here's what we're going to say. We're going to say that x is equal to 4 inches. I already said that. And we're going to say that delta x our error is equal to 0.03 inches, but that's also equivalent to dx according to this format. So we're going to throw the numbers in now that we've got the values. So S was originally 96 inches squared plus ds. I don't know what ds is right now. And this is 96 inches squared plus, now we've got 12. What's x? X is 4 inches. 4 inches. And then dx is 0.03 inches. So we just multiply this out. Now you notice you can kind of take the 96 off of both. You end up getting ds is approximately, so I'm going to just remove those. That's the original. But 12 times 4 is 48. And 48 times 3 is 154 with 2 decimal places. So that's 1.54 inches squared. Okay, so 12 times 4 times 0.03 is, whoops, I got it wrong, 144. 144, okay? So 1.44 inches squared. So that's the alteration in surface area. Now, what if you need to know the percent? Well, you would take the error, so this is basically considered the error, and you would divide it by the original. So the percent is equal to the ds over the s. So 1.44 inches squared over 96 inches squared. Notice the inches squared cancel. If I get a calculator out and go 1.44 divided by 96, I've got 0.015. So that's equal to 0.015, or move it over, you've got equals 1.5%. So that's our percent error. If we want to talk about it that way, 1.5% error, that might be too much for whatever kind of engineering process you have. So you would have to fix your machine, calibrate it a little bit differently. So that's how we can find error propagation.